Hi everyone, let us discuss design of eccentrically loaded columns. Columns are normally designed for axial loads. However, in practice, it is very hard to apply load directly on the neutral axis. Most of the time, the load is eccentrically loaded. Hence, in addition to the axial stresses, we would have flexure stresses developed in the columns. Therefore, the eccentrically loaded column topic is very relevant to today's discussion. As we know from our combined stresses knowledge that the stress distribution acting over a cross-sectional area having both axial load and the bending moment can be added together by taking the contribution of axial stresses and the flexure stresses. Thus, the maximum compressive stress will be equal to P by A plus MC by I, where P is the axial load applied, A is the area of cross section of the column, M is the moment when the load is applied off center. C is the distance of the fiber at the extreme end from the neutral axis, and I is the moment of inertia of the cross section. This maximum stress has to be less than the allowable stress. Allowable stress is actually the stress which a particular cross section can sustain. This brings us to the interaction formula. As we have discussed that in the case of eccentrically loaded column, we have an interaction of axial stresses and the bending stresses. So it is important to achieve a balance between these two effects. In order to do so, we normally separate the contribution to the column area by the axial stress or the axial force and the moment. So the contribution of area required to take the axial load would be equal to P by sigma axial allowable, where sigma axial allowable is the allowable axial stress. Similarly, if the allowable bending stress is taken as sigma b allowable, then our contribution of the bending area will be mc by sigma b allowable by r square, where r is the radius of gyration of the cross section. So we can write that the axial area contribution plus the bending area contribution must be less than or equal to the total area of the column. Plugging the values of the axial area and the bending area, and after some algebra, we will get sigma A by sigma A allowable plus sigma B by sigma B allowable must be less than equal to 1. So in this equation has been obtained by dividing our combined area equation by A and then carrying out some algebra. The sigma A allowable is the axial stress given by the formulas which we discussed in MOS 1. Sigma B allowable is actually the bending stress normally supplied by the codes. Let us study this example to make things more clear. So we are given a column that is made up of aluminium alloy 2014T6 and is used to support an eccentric load P. Determine the maximum magnitude of load P that can be supported if the column is fixed at its base and free at its top. So this column is made up of aluminium alloy. In section 13.6, we are given design of columns for concentric loading. In this, if we come down, we are given some formulas for aluminium columns. According to this formula, if the slenderness of an aluminium column is between 0 and 12, then we can use the allowable stress equal to 28 ksi. Similarly, if the slenderness ratio is between 12 and 55, we can use this formula, which is 30.7 minus 0.23 KL by R. And finally, if KL by R is less than 55, then we can use sigma allowable is equal to 54,000 by KL by R square. So for these equations, we have to first of all work out the slenderness ratio, which comes out to be 277.1. Now, 277.1 is greater than 55, therefore we can use the equation 13-26 to get our allowable stress. So allowable stress is 54,000 by KL by R whole square. And plugging the values, we will get 0.7031 KSI. Now, using our previous combined stress equation, which is over here, we will write it in terms of P. And from there, we can get sigma max equal to 0.3125 P. Please note that area of this cross section is already known. The eccentric moment PE will come out to be in terms of P. We already know the eccentricity as we know the location of this load on this on the cross section, and moment of inertia of this cross section can easily be found. So everything is known, and this equation will come out to be in terms of P. Now we can compare this equation with the allowable stress determined earlier, and from there we will get P is equal to 2.25 kips.